In this video, I'm going to introduce Module 3, pages 160 through 166. Again, we're working with linear equations, the equations of straight lines. We're also dealing with linear inequalities, greater than, less than, greater than or equal, less than or equal of linear straight lines, so linear inequalities, and how to graph, create tables, equations or inequalities, and word problems. And again, given any one of the four, being able to find the other three. So page 160 just gives a scenario, but there's nothing to solve on it. You can use graphs to estimate solutions to inequality problems. Use the graphs to estimate the times deep flight 1 will be more than 1,400 feet below sea level, and the times deep flight 1 will be less than 1,400 feet below sea level. And so for each of these graphs, the relationship, the time in minutes, and the depth of deep flight 1. The rectangle on the left shows the set of all depths for deep flight 1, less than 1,400 feet below, and the oval on the right shows the set of all depths for deep flight 1, more than 1,400 feet below. So again, 1,400 feet below sea level is right here. So they drew a dashed line, or a line out to where it meets the line of the graph. And then they brought one down from the time. And it's about 3 minutes, so it's really close to 3 minutes in. One thing, again, to be careful of, I mentioned this in a previous video, when you're dealing with negative numbers, 0 is bigger than any negative number. -1 is a bigger number than -2, -3, -4, so forth. So with negative numbers, the further you are away from 0, the smaller the number. -1 million is a lot smaller than -1. Just keep that in mind when you're dealing with greater than or less than, because sometimes this causes some confusion. So, the times where deep flight 1 is greater, so greater than 1,400 feet, well, in 0 to 3 minutes, approximately 3 minutes, it's greater than that depth. And after 3 minutes, over here, it's deeper. It's lower than 1,400 feet below sea level. Or I could say its depth is more than 1,400 feet below. 1,500 feet, 1,600 feet, more than that below, because you're talking more of a negative. So again, be careful with the terminology. It can be confusing. Just create a mental picture of what you're looking at to be able to describe it. Deep flight 1 will be greater than 1,400 feet in less than 3 minutes. Deep flight 1 will be less than 1,400 feet for times greater than 3 minutes. Let's take a look at the problems that they're going to ask. On these, I'm going to do problem A, and I'm going to let you do problem B. And so, use your graph to estimate when deep flight 1 will be less than 2,100 feet below. So, let's find 2,100 feet below on our chart. It's right here. So I'm going to draw a line out to where it intersects our graph at negative 2,100, and then I'm going to come up from that. Well, I'm pretty close. It's not far from 4.5. So I'm going to say it's about 4.5 minutes. So less than 2,100 feet from the start of the dive until approximately, because all we are is close on this, on graphs. Approximately 4.5 minutes. deep flight 1 is less than 2,100 feet below sea level. Or negative 2,100 feet. I'm going to let you write out for more than 2,100 feet. But again, that 4.5 is going to come into play. Write an inequality and solve it to determine the time. So for 2a, well, we want to know, we're dealing with 2,100 feet below, and we want to know when or how long it's going to take to reach that at our current speed at diving down at 480 feet per minute. So when is 2,100 feet less than? Like how many minutes does it take? I could have also written this the other way at negative 14 or negative 480 t. And so we need to isolate that t, divide both sides by negative 480. And this is where a calculator comes into play. (2100) negative, divided by negative 480, 4.375. I'll do that in blue. 4.375, and we're dealing in time, so minutes. Oh, we divided both sides by a negative, so that sign is going to flip direction. So the time less than 4.375 minutes. Because again, 4.375 is on the big, and we need to be less than that. And so I'm going to have you solve 2b and take a look at it and figure out, what you want to put for 3. How do your answers using the graph compare to those you wrote when you actually solved it? Again, when we did up here, we approximated 4.5. When we solve it, we get the exact number, 4.375. I'm going to start page 162 with you, and then I'm going to turn you loose on the rest of the pages and problems. So let's set up this scenario and this table together, and then see if you can use it to answer the questions that follow. Deep Flight 1 can dive to a depth of 3,300 feet below sea level and can ascend, so we can go down to negative 3,300 feet and can ascend. To ascend is to come up to the surface at 650 feet per minute. So a rate of positive 650 feet per 1 minute coming up. So that's going to be a positive graph. Suppose Deep Flight 1 is going to ascend to sea level starting at its maximum depth. So again, we're starting at 3,300 feet below sea level, and we're going to rise at 650 feet per minute. identify the independent and dependent quantities, define our variables, and write an equation to represent deep flight's depth. Well, let's go let D equal depth in feet and depth depends on time, so that is our dependent variable. And then we'll use a T for time. Again, it really doesn't matter what letters I use as long as I'm consistent with my problem. And I have to define the quantities. Time is going to be in minutes. And I chose minutes because they said it rises at 650 feet per minute. And they said 330 feet below, so those are my units. Time in minutes is my independent. On a graph, my dependent is my y value, and my independent is my x value. And so, in terms of total depth, depth is, how fast do we rise? 650 feet per minute. And what depth are we starting at? We're below the ocean, 3,300 feet. So I don't need to put the units on my equation. So my equation then is depth equals 650 times the number of minutes minus 3,300. That's my start value. On a graph, again, I'm just dealing with this quadrant right here. This is time in minutes. It's just going out positive. And my depth is starting off down here. When x is 0, y is negative 3,300. And we're going to be rising a certain number of 650 feet every minute until we reach the surface. Again, we're not going to go at positive elevation. Our submarine's not going to go into the air. The highest it's going to get is 0 when our elevation reaches 0. And time is going to be a positive time. It's going to be somewhere out there, but I'm not sure how many minutes that's going to take yet. So what quantities are we dealing with? Our independent quantity, we said, was time. What unit of time are we dealing with? Seconds, minutes, hours, days, weeks, years. In this case, we're dealing with minutes. And what variable did I use to represent time? I used a capital T. What dependent quantity? What are we dealing with? Depth. What is depth being measured in? What unit? Feet. And what letter, what variable did we use to represent depth? D. When we're starting out, how deep are we? What depth are we at when we're starting this? In this case, we're 3,300 feet below sea level. And after one, so as this is going up 1, as our x value is increasing by 1, our y value, how fast are we rising? We're going up 650 feet every time. And so what is negative 3,300 and add 650 to it? Again, 3,300 bad guys, 650 good guys is 2,650. So we came up that amount. We came up 650 feet. We're getting closer to 0. And we come up another 650 feet, and now we're 2,000 feet below the ocean. We come up another 650 feet, and now we're 1,350 feet below. We're getting closer to the surface. We go another 650 feet, and now we're at 700 feet below sea level. We go another 1 minute, and we come up 650 feet, and now we're 50 feet below. And so a little more than 5 minutes, we're going to be at the surface because, again, at 6 minutes, if we continued that and we're like a duck and could go into the air and fly, we would be at 600 feet above sea level. But a submarine, since it can't fly, has to stay at the surface. All it can reach is 0. Why does the table end at 5 minutes for this problem situation? It doesn't make sense to put it at 6 minutes. It doesn't make sense to use 6 minutes since we'll reach the surface, we'll reach 0 prior to that. We'll reach the water surface. Which is 0 feet before 6 minutes. What do you consider the possible values for time and depth? What do you think are all the possible values for time in terms of the situation? Write an inequality to express your answer. Well, again, the time, it's going to be just a little more than 5 minutes. And so, but I know it's less than 6. So our time has to be less than 6 minutes. So our time has to be less than 6. And I could come a lot closer to that if I want to actually solve the equation and find, maximum when we're at 0. I could put a depth of, again, my equation is d equals 650t minus 3,300. Well, how long does it take to reach 0 when depth is 0? 650t minus 3,300. Add 3,300 to both sides. I'm going to rewrite it up here. 0 plus 3,300 is 3,300 equals 650t. Over here, these guys just canceled out. They created a 0 pair. So 3,300 equals 650t. I'm going to divide both sides by 650. Division property of equality. That's a fancy one. And 3,300, again, great use of calculators. 3,300 divided by 650 is approximately 5.08. Now this is less than 5.08, so I'm going to say t is less than 5.08. And if I wanted to be more precise, I could put the equal sign. I could say t is less than or equal to 5.076923, but I know 5.8 is more than that, so I know t is less than that. All right, I am going to turn you loose now using the table and that information, and see if you can work on pages 163 to 166. And I'll be posting the answers to those in a couple of days so you can check your work and let me know if you have any questions. Good luck.